Thank you, Chairman, and thank you, organizing committee, to give me opportunity. I'm an experimentalist, and it's really thrilling to have introduce one of our new Tokamak to the simulation community, so that we can have some more work. So the points to be discussed: why fusion is future. So already it is already introduced how the Tokamak operates and how the different confinement and Lawson criteria has to be taken into considerations for fusion by Professor Ganesh. So I'll be quickly covering that. Then I'll be introducing what is a spherical Tokamak. It's a new class in Tokamak, and introduce the new spherical Tokamak in IPR and some first plasma experiments that we did and some future perspective. So there's no doubt that energy security is the key for the future, and if we see that most of the, there is no low energy and rich countries, and India is now aiming for the next, next future few decades will be of India's. Multiple reports, they say that predict that India will be the second largest economy, and if you are going for 50 or 100 trillion economy, you need a tremendous power requirement. And we have energy mix is the key issue here. Although we have the solar, already we have 30% achieved in India, the solar. But all the heavy industries and manufacturing sectors, they need the high energy density sources, and the non-continuous energy sources like solar or wind cannot cater to that. As we know that only it's available in the daytime and not continuous enough. The intensity varies over the day and also throughout the year. So the fusion is one of the promising source where we can really get an unlimited amount of energy. And here we fuse two lighter elements like hydrogen or deuterium and tritium, the isotopes of hydrogen. And why in laboratory we choose the deuterium tritium? Because it has maximum probability of fusion, the cross section at a lower temperature. In sun, it is already driven by the heavy high density and magnetic gravitational pressure. So as Professor Ganesh introduced that we have some Lawson criteria which needs to be satisfied to net energy gain Q is greater than 1. Although it is less than this NT, tau combinations, multiplications, you will have fusion. Fusion will be always there. But the amount of energy you are giving input to the fusion machine and the output which you are getting, so they will not be balanced. So they will be balanced at the Lawson criteria. So in experiments on Earth, we have already few machines we achieved very close to the Lawson criteria. One of them is JT60U in Japan. And to give a perspective, the sun is already 10 to the power 20 times higher than the what Lawson criteria says. And you know that because of enormous confinement time that sun has, that is around 10 to the 12 seconds, the energy which is generated in the core of the sun, it takes this many million years to come out of the sun. So virtually the fusion is unlimited source, unlimited energy, and practically zero carbon footprint as far as the reactions is concerned. And there are various different type of fusion concepts. Tokamak is always a front runner, although the physics and engineering they quite overlap with each other. And many of the physics what happened in stellarators are actually applicable in the Tokamak and vice versa. And many of the auxiliary heating systems, diagnostics, controls, they are more or less similar. And Tokamak already Ganesh explained that why we need different type of magnetic field to confine the plasma. So main is ohmic coil, which generates the electric field to generate the break down the neutral and drive a current. And the toroidal coils produces a magnetic field, which is the primary magnetic field to confine. But we need a twist in that confinement, magnetic lines, and that given by a plasma current which is induced in the plasma. So in Tokamak, for a stability and a high confinement, stable plasma, we need, absolutely it is necessary to drive a current. And as long as current is driven, we'll have a hot temperature, high temperature plasma in the Tokamak. So we have remarkable progress in fusion in last 3 to 4 decades. So recently in 2023, you might have heard that one of the highest record of long pulse operations, because for fusion reactor we need a long pulse operations. In the early 90s and late 90s, we have already achieved, there are 2 parameters. One, x-axis is the plasma durations, how long you are confining the plasma, and the y-axis is the Lawson criteria, the NT tau, that how good the number is to achieve a fusion. So this is the Lawson 10 to the power 0. We have already achieved in many Tokamaks, but recently we have, they are not for long pulse operations, but now we have already long pulse operation of 1000, more than 1000 seconds, at least for 2 Tokamaks. And if you see there is remarkable progress until the early 2000, but there was a little bit slowdown because most of the efforts, money and concentrations went to building the ITER, that is the largest fusion project in the earth. And that has been probably compensated by the last, in 1 decade or so, the amount of private investment which is now happening. So that is a good sign. So as I mentioned that we need a steady state current drive that is should be non-inductively, because in ohmic based systems you cannot, it's a solenoid kind of system which has a maximum pulse durations limited by the engineering point of view. So we need RF and microwaves to do the job that it can drive. And recently in the East Tokamak, people have already demonstrated up to 1000 second continuous straight flat plasma current drive, and with a good confinement, of course lower than the Lawson criteria, because in this experiment it was the motivations was for long pulse sustainment. So there are many still physics and engineering issues which has remained to be resolved, but one of few of the interesting is fully non-inductive startups by electron cyclotron waves, or a mode converted electrostatic waves like Bunsen waves. And as you know, the energetic electrons, they are the real problems in Tokamak confinement, stability, and also the plasma wall interactions. So what are the different ways we can, these energetic electrons we can confine and drive them to help us not in the deteriorating the plasma operation. And also high beta operations needed is because the high bootstrap action. Bootstrap is the self-sustained currents generated due to the pressure gradient, which Ganesh already mentioned, and economical shaped plasma. So all these 4, at least the concepts are very attractive in a spherical Tokamak configurations. So spherical Tokamak is like the, this is the magnetic, toroidal magnetic field 1 by R fall from the center stack. And the conventional Tokamak plasma sits away from this axis, so not using this magnetic field. Whereas the spherical Tokamak, it is the both side squeezes together and they utilize this gradient, very high gradient. So these are compact size and can be operated in low magnetic field, so utilizing less pressure on the power supply. And they're also attractive for fusion startups. Some of the fusion startups are actually now taking this path because it is smaller in size, and you can produce and sustain similar type of plasma, high temperature plasma at a lower cost. And one of the key requirement of fusion is sustained fusion is shaped plasma operations. And in spherical Tokamak, this shaping, that is, this is the elongated or the triangular shape, comes naturally. And also high beta operation is possible, which induces a self-sustained current. So to leveraging, we have in IPR already, we have a strong legacy of the conventional tokamaks like Aditya Upgrade and SST1. So we have a good expertise, and to taking that advantage, a small scale lab ST has been proposed, and it was built and made operational last month. So that I will introduce. So this is the first spherical tokamak device in IPR. So device parameters, I will not go into details, so you can have a look that compared to this human, how big or how small it is. So it has 6 toroidal field coils and 6 ports. It has central solenoid, but in spherical tokamak, central solenoid space is very limited. So that's why more dependency on the RF and microwave driven plasma current is required. So the inaugurations, this machine was built after all the equipments came into IPR supplied by the vendors. So the total time taken, the young guys in our group, so they took almost 7 to 8 months to build this machine, and all the different systems and subsystems were tested independently. And on 11th December 2025, this machine was inaugurated by Director and Deans, presence of all our scientists and engineers. And the vessel pressure on that day was 10 to the minus 7 millibar, but now as I am talking, it is already reached minus 8 millibar. So the first plasma parameters is like this. We injected the hydrogen gas. The operation sequence starts from injecting a hydrogen, and this pressure increases, and once it reaches the flat top value, we start the toroidal field coil charging. And once the toroidal field coil charge current is flat top is reached, then we inject a 2.45 gigahertz microwave power to initiate the nuclear neutral breakdown, and which is required because the available loop voltage is smaller than the expected. I will come into that aspect. And this is the loop voltage, that is the ohmic system started to produce electric field inside the tokamak vessel, which will drive the plasma current. So a view of the first plasma, which is seen by first camera, is like this. So we have the breakdown of plasma, and as you can see, these blue lines are actually the H alpha emissions, and you can count that for each time the H alpha is peaked, because the plasma moved outward and hit the outer wall, because it was not a very well controlled plasma. We only took 3 shots, and we need to study more to how to control this and keep it steady at the center. And okay, so during the ohmic discharge phase, with strong filamentary filaments are observed. These are quite in spherical tokamak, especially these open field line configurations in the outboard side, they give these filaments, thick filaments, but we need to study the origin of these filaments and we have because of this probably means it's very early to say the density was sometimes over dense, and 2.45 gigahertz could not penetrate, and that is why we see a periodic absorptions of EC waves and periodic bursts of plasma. So this can be evident from here. So whenever there is a high power and low, this is the stray radiated power, which is unobserved power of the 2.45 gigahertz. Only during that time we have a strong emission of all signals, like all impurity signals, H alpha, C2 and C3 and O2. And one of the interesting things which we observed, that in this machine we have the toroidal vessel is continuous. So unlike Aditya or Aditya Upgrade, we have a toroidal break. But in this machine, the vessel is continuous, and the plasma and vessel wall distance is very small. So during in the previous slide which I showed, so during this high rate of change of ohmic coil currents, so there will be change of flux enclosed by the vacuum vessel, and that will induce also a voltage. And since it is toroidally continuous and resistance is less than 1 milliohms, a huge amount of current is expected. So initially we didn't have any measurements system to measure the vessel current. So we just, our team members, Sheetal, she did some simulations of simple filamentary approach that taking into the few active coils where the current is flown and the vacuum vessel as number of filaments, approximately 200 passive filaments, and where the voltage is induced, and to estimate what is the total current. And the total vessel current, we were very surprised that it is up to 125 kilo amps. So initially I didn't believe that in this machine where we intended to produce only around 30 to 40 kilo amps of plasma current, and the vessel current could be so high. So then we did some measurements. Initially we tried to find out that whether this vessel current that is also produce a magnetic field, and whether that magnetic field can affect the available loop voltage or not. And yes, we found it indeed true. So this is the measurement of loop voltage, and this is the simulated, that is with vessel, and this is without vessel, because we cannot do an experiment without the vessel. So in both the situations, this remains same. If you see that the simulation without vessel, the loop voltage is actually higher, close to the 8 volt, and around 1 volt drop because of this vessel current. And there is also additional delay in the loop voltage, and that is also we have seen in SST1, that is also superconducting machine and continuous, toroidally continuous vessel. But this we could see. And then we in the last month we tried to measure some vessel currents by a new method, is fiber optic current sensor. That means a optical fiber is wounded through the vacuum vessel, and a laser, polarized laser is injected through it, and as the magnetic field appeared because of the vessel current, so the polarization plane will shift, will rotate, and measuring that rotations, we can accurately measure what is the plasma current. So in that, we have the peak values are different. What we observe analytically means numerically we simulated and the measured. The measured was around 262 kiloamps, and of course the final calibration is pending, and the vessel current was 126 kiloampere, that is simulated. But in the normalized shows that both agrees excellently, at least the qualitative wise. There are some discrepancy here. We are looking into what could be the reason that some of the filaments or local eddy currents which are flowing, and that may be affecting this mismatch. And we also took a sample measurement just to see that whether actually a vessel current is flowing through the outer layer or not, outer body or not. So we put a simple copper bar and put a CT, and we saw the yes, and this CT measurements, which is absolutely calibrated, and taking only one filament at the outboard side, that simulation shows very good agreement, over 25% of agreement of the values. So we'll be doing more work on this, just to have to see that how much magnetic field is produced by this induced vessel current of around 125 kiloamps, and we see really quite high magnetic field which can affect the breakdown, which can affect the initial plasma startup and initial equilibrium. So we need to carefully design some compensating coils to mitigate this effect. And so we are also planning to have some in-vessel measurement inside this in one RZ plane, so that we can compare the estimated value and the measured value. So now the ST device present status is, we are in last 1 month we are doing some wall conditioning experiments to create a better wall by reducing the gas partial pressures of different impurities, that is that will be necessary to create a plasma current. And we are continuously doing some GDC. Okay, so GDC is I'll just show So this kind of a rod which is pneumatically activated. So when we do the GDC, during the plasma shots, this GDC rod is actually retracted remotely, and when we do the glow discharge cleaning, we insert it back and do the cleaning by applying some DC voltage. We are also started with injecting some microwave 2.45 gigahertz, superimposing with this, and we are expecting good results for wall cleaning. And this is one of the first view of glow discharge. Initially, we started the discharge in higher pressure range around -2. That's why you saw some sparking kind of thing, and then immediately the pressure is reduced to -4 range, and we have a very nice uniform plasma. So one of the interesting feature of spherical tokamak is its good curvature and bad curvature of magnetic field lines. So in conventional tokamak, if you remember I have shown the 1/r profile of the BT. So the toroidal field in the inside of the tokamak and outside, that is low field side and high field side, so they are not much gradient. But in the spherical tokamak, since the plasma is sitting very close to the axis, so we have a very strong gradient of toroidal magnetic field. So the magnetic field, the field line pitch in the inboard side is very small, and while the outboard side is small, and outboard side is very large pitch. So the particle stays much more time in the good curvature region, so that is why it gives the stability. And with different type of poloidal field coils, we can produce different curvature of the magnetic poloidal field, curvature of the magnetic field. This is an example of quest tokamak where by energizing different set of PF coils, we can produce different curvature, and which is characterized by something called mirror ratio that defines that whether the energetic electrons which will be generated by the fundamental and second harmonic ECRH, when we inject, they will be trapped or not, what Ganesh was explaining. So yes, trapped particles he has already explained. I'll just show this cartoon. I took it from the East websites. So with this, each banana orbits, the particles, the stagnation point actually shifts toroidally, and this is called toroidally precision. And these toroidal precisions could be used to drive a plasma current fully non-inductively, and that has been demonstrated in few of the spherical tokamaks especially. And such type of large banana orbits could be produced.
Sure, you have 2 minutes.
Okay, yes, thank you. So, so one of the example is if you carefully design the poloidal field configurations and mirror ratio in such a way that, so some co-moving electrons with stagnation point, that is have a precision toroidally, preferentially in only one direction, then current could be produced. So in this velocity space plot, so in both these are trapped electrons, energetic electrons, and but in only in co-directions there is a bunch of electrons which are actually toroidally precise. And utilizing this, we have demonstrated that a plasma current could be driven fully non-inductively. In this experiment, there was no loop voltage or no ohmic system was applied. The plasma breakdown was happened, initiated with 8.2 gigahertz ECRH, and the current is completely driven by the second harmonic, 28 gigahertz, around 270 kilowatt, up to 50 kiloamps per couple of seconds. So our next target is to actually collaborate or do together with that some guiding center orbit codes, and try this to find out the best possible configurations so that we can utilize this trapped particle effect. And this new ST device now, it's designed and built proudly by the second generation's scientists and engineers, ably guided by the experts. And it is proudly made in India. Almost all components are designed by IPR scientists and engineers and made by all domestic industries. and it is dedicated to the next generations because we want to make it, because since it is a smaller device, so it has a very quick turnaround time and less risk of failure, so less burden on the students and the new researchers. So they can think freely and do the experiments, and it will be fully supported, all crazy ideas. So with this new device, now IPR becomes the only institute in the world which has having currently 3 operating tokamaks, that is Aditya Upgrade, SST1 and this new ST device. The name of this new device is still pending. We will be doing shortly. So I'm concluding with a fusion SWOT, that is strength, weakness, opportunity and threat. We know that we have full strength, and the only weakness is it's not matured enough to produce electricity. And now we have a good opportunity in India because the nuclear code is now more liberal, so more private participations could be possible. And we also saw a good amount of progress in all over the world, the amount of funding which is now given by the private players. And of course, we have some threat, that is inconsistent funding or inconsistent policy decisions, that what we exactly want to do. This I will not explain. And conclusion, so this is the team that built a ST device, and behind this, and a small video how the device made from the scratch. With this, thanks.
So thanks to Kishore, who is heading this program and made this machine in such a small time, and all the entire team members. And this is the first, spherical tokamak, so we are really proud of it. Hopefully some new interesting results will come out from this machine. So now time for the questions. Yes.
Well, many thanks for your nice talk, and I'm happy that you have commissioned the machine last December. So I believe it is in, benchmarking stage and kind of this, right? Or because spherical tokamaks are already in use in several countries and several institutes. So what outstanding issues primarily you'd like to investigate with this, and how long it will take to go into the operational stage?
Yeah, it's a very good question. Thank you. So one of the outstanding issues which the conventional tokamak or the spherical tokamak remains to be resolved is fully non-inductive current drive, and driving the current and hitting the core of the plasma in a overdense condition.
Non-inductive meaning bootstrap?
Non-inductive is without the use of any central solenoid.
So okay.
It's fully electron
like
cyclotron driven.
So it's like a bootstrap kind of things?
Bootstrap is a consequence of central heating and a pressure gradient which will be generated inside the tokamak. That could be driven by many other different auxiliary methods. But most of the future machines will be overdense, operated in overdense conditions. That is, the injected wave is the omega will be less than omega PE. So the EC waves cannot inject it. So that is a methods called mode conversions, which the electromagnetic modes could be converted to the electrostatic modes in the edge of the plasma, and it will be fully observed at the resonance layer. Those things could be investigated in this machine. Yes.
So, hello, Kishore. First of all, congratulations to you and to your team for making it. So, couple of questions. Number one is like whether the future tokamak will be ST, or is it going to be like this one, the conventional one? Next is that how far, final goal is that you have to deliver electricity through this machine. So from the technical perspective, you have a very small, compact, inner, where the windings and other things, heat loads, and you say that the size of the machine is going to be smaller, and where we know that ITER is such a big, system requirement, the physics behind it. Okay, so that is one question. And another, I was surprised that when you have done some simulations, modeling, why you, didn't consider that you did not have a brake, electrical brake of the systems. So while designing, you made it, thought that like it is okay, or how did you arrive at?
Okay, so I really cannot, I don't know that the future fusion reactors will be conventional tokamak based or the ST based, but definitely it will be tokamak based. And both CT and ST actually complementary to each other. Although some companies and at least especially in UK, the spherical tokamak based fusion reactors is now being pursued and proposed. But we believe this machine will be dedicated for training the manpower, because we have a lot of younger generations researchers which we need a machine where without any complications you can get much amount of machine time and do experiments to study tokamak, startup tokamak physics, equilibrium, and put some diagnostics and learn it. So this will be mostly used for this purpose. And your second question was for about the toroidal. The toroidal vessel current has both pros and cons. I didn't discuss this. It could be, yes, it stabilizes the resistive wall modes and long range kink modes in one aspect. The second aspect is it's the controlling the plasma by external coils, magnetic coils will be a bit difficult because of the delay. And in NSTX kind of machines, people have seen that because of this large vessel current, the toroidal rotations also is stabilized. It reduced. And we know the toroidal rotations required for improving the confinement and achieving the H mode. So kind of both pros and cons are there, so we have to carefully adjust. Yes.
I'm Anshu Verma from TFR Hyderabad. So I just have two questions. So I might have missed, I want to know why do you want to switch from 2.45 gigahertz to the higher frequencies? And I assume this will change your the ionization region where you will create first time your plasma. So will it affect the output of your machine later? And second, my question is, well, you are comparing with the simulation, which platform do you using there, and do you account for the ionization mechanism also while doing those simulations?
If here I have not correctly understood, please forgive me. The first question was probably the 2.45 gigahertz. So that choice came from the toroidal field, magnetic field, which the machine is designed. So it was for around 0.1 Tesla. So the 876 Gauss is the nearest for 2.45, so we use the 2.45. But one of our next operations will be also aimed at fully only ohmic driven breakdown. If we stabilize the vessel current, induced vessel current, that effect, then we can probably broken down the neutrals only ohmic. But the 2.45 and the other higher frequencies will be in future will be utilized to drive a plasma current, because our ohmic pulse is only short, very short duration, because your center stack dimension is very small. So a non-inductive current drive and EBW experiments will be done by EC only. So it will be mostly like 2.45 and 5 gigahertz in the future.
Okay.
And your second question probably was about the vessel current measurement. I could not follow. I will discuss it later.
Okay. Thank you, sir.
Okay, thank you.